My name is Turan. Hello, everyone, ladies and gentlemen. I am from the Center for Solar Energy Research and Applications. It's in Ankara, Turkey. I will be presenting some of the results my students have recently obtained and also make an introduction to PV manufacturing in Turkey, and also introduction to our research center. And I will touch a little bit on nickel metallization and BC fabrication at our center. Well, Turkey, or Turkey with the old name, Mr. Trump has been joking on our name, Turkey, because you know Turkey is the name of an animal. So this is why we have changed the official name from Turkey to Turkey. So we are trying to get used to this new name. Okay, it is located in the intersection of three. Yeah, he did a joke a few days ago, I mean, about Turkey, you know. Well, Turkey is located in the intersection point of three continents, Asia, Europe, and also Africa. We have good connections with the surrounding countries. We have good relationship with all of them. There is a good solar potential there, and a large population, large domestic market, and also low production cost for PV manufacturing and low carbon dioxide footprint. So with this, Turkey is emerging as an attractive manufacturing site for PV industry. So we see this from the recent activities in Turkey. So we have many module makers in Turkey, more than 50, maybe. We cannot count them. And for the ingot and wafer manufacturing, Kalyon PV has been producing PERC cells for the last 5 years in Ankara, in the same city as we are living. And they are now upgrading to TOPCon. CW Energy in the city of Antalya, they have just started production of TOPCon solar cells in Turkey. This is the first line in Turkey, also in the whole region, actually, for this technology. The line also includes 1.2 gigawatt wafering. And Smart Energy is another company producing PERC lines in the western part of the country. And Fellow Energy is a Chinese, 100% Chinese company. They are starting up a new line in the southeast of Turkey. And 5 other companies are now preparing new manufacturing lines. And among them, Astro Energy is 100% Chinese. All others are also somehow involving Chinese partners in their project. So there is a very strong Chinese involvement in the PV production in Turkey. Other than these, we see a lot of activities in manufacturing of encapsulation materials, glass, inverters, etc. So as a result, Turkey is now covering almost the whole value chain in the PV manufacturing. Well, with these results, so we see that Turkey is becoming the biggest PV manufacturers after China and India in the world, probably in the coming 5 years. So if all these projects are realized, so the total capacity will reach about 40 gigawatts, so which is a good number for our country and for the region. Well, in parallel to this, we have developed a new research center facility in Ankara. And it is the most comprehensive and maybe most advanced research facility in our country, as well as in the whole region. So this is one example from facilities from our research center. This is showing the production line, crystalline silicon production line. It is now processing M2 wafers currently. We have all the processes, so we can process starting from wafer up to the cell. Fabrication, all possible processes can be realized. So with this, we are acting as a consultant, technology provider, technical provider, and R&D provider to the companies in Turkey as well as in other countries. So currently, we are upgrading the line to M10 G12. So these are our new babies. They are now in the Shanghai Harbor. They are being shipped to Turkey in these days. It is 8-tube system. It's a new production platform for G12R and M10 wafers. Songyu Technologies and Eurosolar together are organizing this facility. So it will be operational in March 2026. So I just skipped this one. Many people have already analyzed the market development in the coming years. So I just come to this, some more scientific technical stuff. So when we look to the new generation of high efficiency solar cells, we see that fabrication of polysilicon finger or patterning polysilicon is the key process in both TOPCon and also in the BC fabrication. In TOPCon, we are talking about local emitter on the front side and local BSF on the back side. So this seemed to be next stage, maybe in the advanced TOPCon manufacturing. Some companies have already implemented this, especially on the back side, so it is commercially available. For the BC case, we have, of course, poly fingers on the back side. So patterning poly is a critical parameter, a critical process, and this will be also remain critical in the next technologies like 3T tandem. So we will still have the patterning on the back side. So this has been successfully done by laser ablation so far. We have seen a lot of approaches using laser ablation by companies, also by institutes, including including ISC. Well, okay, I would like to present some alternatives today. One of them is based on printing, actually. This is a kind of inkjet printing, but they call it flex trail. This is developed by Fraunhofer ISE. And we use this technique to print boron ink on the polysilicon and selectively etch the polysilicon to fabricate polyfingers. And also screen printing can be used for the same purpose, and laser oxidation is also well known today. Well, in the more advanced TOPCon structures, of course, it is the polyfingers are useful to mitigate recombination losses in the emitter region, also enhance the selectivity of the metal junction, also reduce the parasitic absorption. So in both front side and both sides, the use of polyfinger seem to be useful. Well, this polyfingers can be obtained by using selective etching by alkaline solutions. We know that heavily doped silicon is very slowly etched by alkaline solutions. So in order to use this property, we created heavily doped, boron doped region under the metal layer by using local boron ink printing. Following the annealing, the structure is etched back. So this region is not etched by the alkaline solution, so the remaining part is etched away. So you create the patterning on the surface. And then we put alumina and silicon nitride to test the passivation. So in this method, boron ink is used. Boron ink is commercially available. It's a very easy commercial product. You can easily apply them. It is compatible with screen printing. Also, it is compatible with inkjet printing, so you can apply this. In this study, we applied so-called flex trail. It was developed by, as I said, Fraunhofer ISE. We worked on this together. And boron ink is applied by flex trail. And it's useful for doping. You can see the doping profiles obtained by using boron ink. So it can be very high speed and also very consistent with finger width. So the results are shown here. So we have obtained very nice polyfingers with the width changing from 24 micrometers up to 100 micrometers. So there is no undercutting. The masking is quite working quite well. So the widths can be obtained in this way. I mean the polyfingers. Well, of course, the passivation is an important problem in here. So we have obtained an average passivation of around 720 in this structure, in the pattern structure. And from this PL image, you see the passivation is quite all right. I mean, it can even be further improved, of course, but the values are still good for such a structure. Well, the second technique is based on screen printing. Screen printing is a simple process, and it simplifies the fabrication. Well, the patterning and alignment are very controlled and reliable, and it's a low-cost technique applicable to both new generation TOPCon and also IBC solar cells or BC solar cells. Industrially variable. In this technique, you just put a mask layer by screen printing and just etch the poly layer down to the surface of silicon. So this is quite controllable technique, and you can, of course, look at, I mean, you can test this, monitor this process using 4-point probe or ellipsometer or optical technique. So it's quite viable and easy technique. And here you see that very sharp edges can be created, and well-defined fingers can be fabricated using screen printing. So it's there is no undercutting. The mask is working quite well, so it is a promising technique. And we actually apply this screen printing technique to fabricate small test samples with these sizes, as you see. And this is the first preliminary results, and it's quite promising. So we have, although the efficiency is low here, we have some problems with the fill factor, so it can easily be improved. So we believe that this technique is a strong alternative to the laser approach. Well, okay, then maybe a few words about the laser process. Here, again, this is based on chemical etching, actually, but the masking during chemical etching can be provided by laser process. You can either use the PSG or BSG layer, just patterning by laser as a mask, or you can oxidize the surface and create fingers by using a laser. So these are known techniques. You probably know about them. We have now used this technique. Just a few words about oxidation route. In this case, I mean, we create the oxide layer by just laser-assisted oxidation of polysilicon layer, and then using alkaline etching, you create well-defined fingers on silicon wafer. So these are all, I mean, just a brief summary of our activities on finger fabrication. So just want to mention a few words about nickel metallization. Nickel is a good material. It's a good metal, actually. It has a good, it has some advantages over copper and aluminum, and diffusion is less and at high temperatures, and it has a good adhesion, and work function can be adjusted somehow. So in this work, which is published here, we have tried two cases. One is pure nickel metal, the other one is silver dope nickel. In both cases, we have reached good, this is, by the way, TOPCon solar cell. So we have reached very similar values, I mean, in the efficiencies. So it seems that silver dope nickel and pure, is very much compatible with, very much competitive when you compare with the standard reference past. But pure nickel is giving us a less efficiency, smaller efficiency, or I mean, worse values, I mean, in terms of other parameters. Of course, this can be, but it is still, I mean, a good number. So we can still work on this and improve this if you want to use pure nickel. So nickel should be considered by industry. So it can be a good alternative to copper. We did a couple of studies like peel force and thermal cycle and damping tests, so they are all good. I mean, the contact is behaving quite good in these tests. So I want to show you this final slide. This is a BC cell we fabricated using standard PN junction without any poly layer, so we have obtained good values for IVOC and JSC, but the fill factors is low. But the good thing with this design that we have very low, I mean, small shading on the backside and high bifaciality. So we have stopped working on this because we will be, I mean, we are focusing on poly fingers and poly-based IBC solar cells. So I come to the conclusion. So, well, Turkey is becoming a strong manufacturing country on PV. Poly fingers are very important in the fabrication. There can be alternatives to the laser fabrication, laser-based fabrication, and nickel is a promising alternative to silver for metallization. So I want to announce this one maybe together with Radovan. So in 2026, Silicon PV will be in Ankara. You are all invited. Please come to Ankara to visit us and to attend this very important conference. So we have very high quality speakers and very good program. So please visit, come to Silicon PV conference. And by 5 PV, this will be 26. Sorry, Radovan. So this will be 26, not 25. I couldn't change it. So this was a picture. So this will be 26. So the by 5 PV will join Silicon PV. So it will be together. So maybe you want to say a few words, Radovan, but so later. Okay. Thank you. So with this announcement, so I want to thank you for your attention.